Okay, we'll start from current slide. Now, first thing I want to know, any questions from anything we've covered so far? And let me remind you again, I'm going to probably say this every class that I think about it between now and the end. I don't have any papers from this class yet, so please don't forget about your research paper. We only have, this is the end of the 8th week, and we only have 2 more weeks to go. Next week and finals, could that be true? Or next week, the following week, and then finals. Whatever, we're running out of term really fast, so don't forget to do your research paper. First test, have I returned those to everybody? I know the last one came in last time, and but it was after I think some of you had left. So here's your first test. And did I get yours right? Okay. All right. Second test. Let's see. Don't have any of those in yet, but be getting those done because we're approaching the end of the term. I'll need those in so we can move on to the third test. Okay. Sorry, I've got conjunctivitis again in my eye, so it's pain in the neck, sort of. It's not the neck. Okay. We're in Chapter 4, Higher Order Differential Equations, and they split 4.1 into several subsections. We're almost finished with 4.1.2. This is a long one, and this is on page 125. And let's see, I don't see, maybe you have an e-book, but let me put this on the board. Definition 4.1.3. If there's no questions, this follows along with the same type vein that we were doing before. Any set y1, y2, y3, ... up to and including y sub n. So you have n, and these are n linearly independent solutions. Okay, if they're n linearly independent solutions of a homogeneous or homogeneous linear nth order differential equation, DE, and you can go back several pages back where they express that equation in its most general form. My eyes are hurting, so it's hard for me to read these things. This is on page 121, right under 4.1.2, that first definition of a homogeneous linear nth order differential equation of that form, okay? On some interval I, okay, is said to be not a fundamental set of solutions. Okay, on that interval. Okay, what does all that blah, blah, blah mean? Okay, first let's start. You have an nth order linear, homogeneous, linear differential equation. Okay, now, how many independent solutions could you have? In fact, must you have n? So you see, this is nth order. If you have n, but they must be linearly independent of each other. If any of these are dependent on one another or more, then you don't have a linear set, you don't have n, so there must be some missing. So if you have n linearly independent solutions to nth order homogeneous linear differential equation on some interval, then that's a fundamental set of solutions. Is it the only fundamental set? No, not necessarily. You could substitute another independent, linearly independent one for one of the others. You can't add any more. You cannot have n plus 1 linearly independent solutions for an nth order differential equation. So one of those is going to be dependent on the others, okay? So that's the most you can have, and when you have all n of them, then you have a fundamental set. And it's not the only one, but it is a fundamental set, okay? The basic question of whether a fundamental set exists for a linear equation is answered in the following theorem. There exists, this is theorem 4.1.4, there exists a fundamental set, I'm just going to shorten that, set of solutions, okay, that's my eye hurts, for the homogeneous or homogeneous linear nth order differential equation, DE, on an interval I. Okay. There does exist at least one set of fundamental set of solutions for a homogeneous or homogeneous linear nth order differential equation on some interval I. There is. There always is going to be at least one. Generally, you could have several different sets of functions that would work. You can't have more than n of them. You've got to have n of them for there to be a fundamental set, but there does exist for every nth order differential equation. Homogeneous one. Now, analogous to the facts that any vector in 3 dimensions can be expressed as a linear combination of the linearly independent vectors I, J, and K, right? Any vector in 3 space you can represent as some combination of those 3 linearly independent vectors, right? Any point you pick in space, I, J, K. You know, you can pick a linear combination of those vectors to represent that point. Okay? Any solution of an nth order homogeneous linear differential equation on an interval I can be expressed as a linear combination of n. If you have an nth order, it's going to be n linearly independent solutions on I. In other words, n linearly independent solutions are the basic building blocks for your general solution. So any combination of those n, linear combination of them, will form any solution you need. Okay? Another theorem. I don't think I'm going to have room for that one, so let me clear the screen. Any questions before I do? Okay? Here's theorem 4.1.5. We're just talking about it. Here it is. Let y1, y2, y3, comma, dot, 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 up to y sub n be a fundamental set of solution. Sounds like we're just saying the same thing over and over. Okay, set of solution of the homogeneous or homogeneous linear nth order differential equation from that equation 6 way back several pages before on the interval I. Okay? If that's a fundamental set, then, this is saying exactly what we're saying, then the general solution of that equation of the equation, the differential equation on the interval, is, this is the general form. Goodness gracious, what a pain in the neck. Y is equal to C1y1, and that's a function of x. Goodness gracious, my nose is itching. Plus C2y2 of x, plus C3 y sub 3 of x, plus ... all the way up to and including C sub n, y sub n of x. Okay. That is your general solution. Any solution that's going to work for that differential equation can be expressed as some linear combination of these of your fundamental set. Okay? Now, remember, if it's a homogeneous equation, right? Differential equation is equal to 0. Okay? That's on the right-hand side. So certainly for that trivial solution, your C1, C2, C3, C4, all those are going to be 0. Okay? Or, if one of these fundamental set numbers happens to be the 0 vector, which would include that, then that C could be anything, or C, your 0 function. Then this C could be anything, all the rest of them have to be 0. So it comes out to be about the same deal. Okay? Now, where C, the C sub I think is what we call it, yeah. I equal 1, 2, 3, ... up to and including n are arbitrary constants. I'm abbreviating like crazy. Okay. Now, another way to look at this is that this states if you have a solution, okay, for the differential equation on the interval, then the constants can always be found so that that solution, if it's a solution, is some linear combination of that the fundamental set. In linear algebra, we call it the basis set. But I keep wanting to say that, but it's fundamental set is what we call it here. They do a little proof here for n equal 2, and you're certainly welcome to look at it. They go back and use the Wronskian that we talked about before, and that forms the basis of the proof. I know y'all probably love proofs, but we're running short of time, so let's do example 7. Do you need this any longer? All right. Here are two functions. y1 is equal to e to the 3x. Okay? y2 is equal to e to the minus 3x. Now, they didn't tell you how they got them. We're going to get to that in just a few sections here. They're both solutions for this homogeneous equation. Y double prime minus 9y is equal to 0. Okay? On minus infinity to infinity, the whole real number line, everything out there. Now, it's easy enough to prove that this is true. Okay? Let's take the first root of that, and what do you get? 3e to the 3x. I'll take the second derivative of it. 9e to the 3x. And 9e to the 3x minus 9e to the 3x is equal to 0. Do that one. First derivative of y2. Negative 3e to the negative 3x. Second derivative would be positive 9e to the minus 3x. Plug that in here. Yeah, same thing. So yeah, those are two solutions. Now, are they linearly independent of each other? Can you form one from another? No. Okay? So they are linearly independent. So That's our fundamental set, or a fundamental set. Okay? Now, I said, just looking at it, you see they can't be done. What we could do is do the Wronskian. Remember what the Wronskian was? I already had you do it, but let's write it down now. Y1 prime is 3e to the 3x, and y2 prime, negative 3e to the minus 3x. And the Wronskian, you remember how that goes? It's a determinant of, the top row is the functions, e to the 3x, e to the minus 3x. The second row is the first derivatives, 3e to the 3x minus 3e to the minus 3x. Okay? And then what we're going to do, the determinant, basically the cross product, but it's the difference of the second one. So it's the product of the first, that would be minus, you tell me, minus 3. And then you do the minus the other one, and what do you get? Another minus 3, okay? Because you had a subtraction there. And that's minus 6. What does that tell you? They're linearly independent of each other. The only way they would have been linearly dependent if that Wronskian had been, say again? 0, exactly. Doesn't matter whether it's plus or minus. If it's anything other than 0, they're linearly independent. If it's equal to 0, they're not. Okay? So that was the other way to show that. Okay? That's not equal to 0. So, can you give me a general solution for that second order, ordinary linear differential equation? Y is equal to C1 e to the 3x plus C2 e to the minus 3x. We have a fundamental set. This is a second degree differential equation. Means you got to have it. You got to have two in your fundamental set. We have them. They're linearly independent of each other. So the general solution will be some linear combination of those. Done. Pretty simple. Okay? That's your general solution on the interval real number line. Okay? Let's do example 8. Can I erase this? Okay, too? All right. Here, oh boy. I really don't care for this one much, but we'll go on and do it because they're doing it the way I would have done it. Y is equal to 4 times the hyperbolic sine of 3x minus 5e to the minus 3x. Now, I really do not care for hyperbolic signs. They're fine. There's nothing wrong with them, except it's just something else to remember. Okay? So what I like to do is write what that really is. It has to do with exponential functions. Does anyone recall what that is? Okay? A hyperbolic sine of 3x is e to the 3x minus e to the minus 3x over 2. Okay? That's what a hyperbolic sine is. So why in the world make up a name for it? Why don't you just use what it is? I'd rather work with that, taking derivatives and other things, because frankly, I have to look up the derivative for hyperbolic sine. Not every time I do it. I know what it is, but I don't want to make a mistake. I don't want to, oh, is this a plus or a minus here? If you do the exponentials, it's going to come out right, okay? So y mess around with another expression. So first thing they do is write hyperbolic sign in terms of what it is. In fact, listed as that minus 5e to the minus 3x. Okay? Now this, of course, is 2e to the 3x minus 2e to the minus 3x minus 5e to the minus 3x, which comes out being 2e to the 3x minus 7e to the minus 3x. Now, why not write the function like this rather than like that? To me, that's a far less obvious way to write the thing. This is the same as that. It takes less room to write it. They're functions I like to deal with. They're easy to integrate, easy to differentiate, easy to deal with. Why in the world write it like that? I don't know. I don't know. I'm sure there's some reason that hyperbolic functions are there, okay? I just don't know what it is, okay? Maybe in one of your majors you'll say, oh, they're wonderful things. They make things so much simpler, okay? Now, they said this function that I just wrote here is a solution of the differential equation in example 7. Well, of course it is. The differential equation there was y is equal to the general solution c1 e to the 2x plus e to the 3x plus c2 e to the minus 3x. Right? That was your general solution. Well, with c1 equal to 2 and c2 equal to negative 7, that's exactly it. So, of course, that's the solution. So, I don't know. I don't know why they decided to put even this one in there. It's just crazy. All you were doing is playing around with hyperbolic signs. And they did say, verify that. Well, you don't need to verify it. Just write out what it is, and it's obvious that it's that. You know, so I don't know. I found that almost a wasted example. All right? Now, they didn't do it the way I did, but to me, that's the way to go. All right, let's do example 9. Here are some functions. y1 is equal to e to the x. Okay. y2 is equal to e to the 2x. y3 is, guess what? E to the 3x. Okay. Not that the subscripts have anything to do, it just happens to be that way. Now, those are linearly independent functions. Okay? So therefore, they will satisfy some third order equation. Here's the one that it is. I get so tired of this. Why don't they show you how to solve it, and then you don't have to go back and do all this mess. Okay, y triple prime has to be a third order, minus 6y double prime plus 11y prime minus 6y is equal to 0. Okay? Now, those functions, they say, satisfy that third order equation. Well, won't take long to do it, but let's do it. Okay? When y1, what's its first derivative? This is hard. E to the x, second derivative. And third derivative? E to the x, okay? So, this will be e to the x minus 6 e to the x plus 11 e to the x minus 6 e to the x, right? Well, all you have to do is add your coefficients and see if they come up to be 0. Because e to the x is never 0. So let's see. 1 and 11 is 12, and minus 6 is minus 12. They add up to 0. Sure, e to the x works. Now, a little bit more difficult, but not super, is the second one. What's its first derivative? 2e to the 2x. Second? 4e to the 2x. And third? 6. So let's do 6e to the 2x. By the way, all I'm going to have e to the 2x's on. So 6 minus.
What did be 8?
Oh, wait. 8, yeah, I'm sorry. Who said 6? Huh? Who? No, okay. 8. Okay, 8 minus, and this was 6 times 4, right? Yeah. That was minus 24. So 8 minus 24 is minus 16, right? Plus 11 y prime, that was 2, so minus 22. No, plus 22. So minus 16 plus 22 is plus 6 minus 6. Yeah, that adds to 0. Okay? Next one going to be just a little bit more, but not bad. First derivative, 3e to the blah blah. Second, 9. Third, 27. So it'll be 27 here. All I'm having to do is 3 x's in them, so they're not 0, so you can ignore that, basically. So 27 minus 6 times 9 is 6 times 9. Well, the second derivative is 9, right? 6 times 9, 54. So that's minus 54 plus 27. That's a minus 27. Okay? 11 times 3, 33. So minus 27 plus 33 is positive 6 minus 6, 0. Yes, those 3 work. Okay? Took a while. Okay? Now, those satisfy the thing. We've just shown that. Well, I said they're linearly independent. We need to do the Wronskian to make sure of that. Now, what I already have done here, remember we said y1 prime was e to the x, and y1 double prime is e to the x. That's all we need for the Wronskian. We don't need the triple prime, just up to double prime. y2 prime was 2e to the 2x, and y2 double prime is 4e to the 2x. Okay? y3 prime was 3e to the 3x, and y3 double prime is 9e to the 3x. So what's your Wronskian? You tell me. Second? E to the x, e to the 2x, e to the 3x. Okay, she did the hard part. Next. E to the x, 2e to the 2x, 3e to the 3x. Next. E to the x, 4e to the 2x, 9, yeah, okay, e to the 3x. The Wronskian. Now, we haven't in this class done a 3 by 3, have we? Determinant. I don't recall that we have. Now, have any of you done determinants before? You, I know, are doing them now. Have you done them? Okay. Do you remember how to do a 3 by 3? There's a little trick. It only works for 3 by 3s. And here's what you do. You do e to the x, e to the 2. What I'm going to do, rather than writing it over again, I'm going to cheat. Okay. Whoops. I'm going to take out that last bar. Okay. And then you write the first 2 columns over again. E to the x, e to the 2x, e to the x, 2e to the 2x, and e to the x, 4e to the 2x. Okay? Now, what you do now is go down the main diagonals, multiplying as you go, and those are positive. Go up the other diagonals, and those are negative. multiplying as you go. So this diagonal gives you what? First do the numerical part. 2 times 9. Help me. 18. Now do the exponential part. E to the 6x. Excellent. Okay, now do the next diagonal. And that gives you, down diagonal, and that gives you plus 3 e to the 6x, right? 6s. Oh, no, okay. Then do that last diagonal, and what does that give you? Plus, my writing is sort of all over the place, but it's this one times that one times that one. Coefficient? 4 e to the 6x. Okay, and here's Lauren. Okay. We're doing example 9 on page 127, section 4.1, subsection 0.2 or whatever. Those are your main diagonals. Okay, positive. Now we do the up diagonals. Now, will it help me to erase the other lines, or can you see this okay? You tell me. Okay, so what's that first one? Because you're going up the diagonal, that's a negative. What? Coefficient? 2. Exponent? E to the 6x. Let's go up the next diagonal, and what does that give you? It's going up a diagonal, so it's a minus.
4.
No, it's 4 times 3. 12. E to the 6x. And then up that last diagonal, and what do you get? Because you're going up, it's a minus 9. That's a 9, right? 9 e to the 6x. All right, we got 3 positives, 3 negatives. Let's add the positives together. That's 7 and 18 or 25 e to the 6x. Let's add the negatives together. That's a minus 21 with 2 more is minus 23 e to the 6x. And that is 2 e to the 6x. But the important thing is what? It's not 0. It's not 0. And since it's not 0, that means these are linearly independent. Okay, I just wanted to do that because we hadn't done one of these in class. And 2 of the 3 of you have done them, but I wasn't sure that it was fresh on your mind. And sure enough, it's 2 e to the 6x, which is the important thing. It's not 0. Okay. Now, these are good. The functions are good. The derivatives are good. Everything's good for all real numbers. Okay? So we can conclude, since we have a third-order differential equation, linear differential equation, homogeneous, we have 3 independent solutions. What is your general solution for this third-order differential equation? Y is equal to? Help me? Help me? How do you get the general solution? C1 e to the x plus C2 e to the 2x plus C3 e to the 3x. If you have 3 linearly independent, or in linearly independent solutions for an nth order ordinary linear differential equation, then the linear combination of those will be your general solution. And that means any variables, values for C1, C2, and C3 you put in there. That's the general solution. Now, any questions? That gets us homogeneous done, right? We worked them to death, right? So let's move on to non-homogeneous. And you'll find out this is not too bad. at least to begin with. Because to begin with, it's just like the homogeneous. Any function y sub p. Now they love giving these little subscripts. Y sub p, now that's free of any arbitrary parameters. Now remember what we mean by that? Those are your C1, C2, C3. It doesn't have those. It's a solution, but it doesn't have a arbitrary constant, okay? Free of arbitrary parameters that satisfies 7. Now, if you go back several pages to 121 again, under 4.1.2, the equation 6 was all that linear nth order differential equation equals 0. That's a homogeneous case, and the identical left-hand side, everything the same, but it's now equal g of x. That's the non-homogeneous. That's equation 7, the non-homogeneous case. So let's say that is this yp is a solution free of any arbitrary parameters. Okay, it satisfies the particular solution of, and that's why it's y sub p, of the equation. Is said to be a particular solution. If that satisfies the equation 7, I'm not going to write it out, but equation 7, then this is said to be a particular solution. Okay. Now, we'll learn how to do those soon. Believe me. I get so tired of playing around with it, but not ever telling you how to do it. Okay? For example, it's a straightforward task to show that the constant function yp is equal to 3 is a particular solution of the non-homogeneous equation y double prime plus 9y is equal to 27. Okay? Now that 27 isn't 0. Okay? So there must be a particular solution that's going to make that non-homogeneous form true. Okay? Now, it's probably not too obvious to you. Okay? If y is equal to 3, right? Y prime is? Y is equal to 3. Y prime is 0. Y double prime is 0. So that's 0, and 9 times 3 is 27. Oh, wow. What a surprise, okay? Now that solution, y is equal to 3, is not given a parameter. It's not given, an arbitrary constant at all. It's just y is equal to 3 is a particular solution for that differential equation. It works, okay? Doesn't have anything to do with the derivatives at all, except that the derivative of it is 0, okay? All right. Now, let's just say that you have a y1, a y2, a y3, you've seen this before, ... up to y sub n, okay? Or y sub k, now they've changed the subscript. Y sub k, that are solutions for the homogeneous case on the interval I, and y sub p, so these are solutions to the homogeneous case, okay, dE, differential equation, and y sub p is a solution, is any particular solution of the 7, the non-homogeneous case. Okay? Now, all right, then this linear combination is also a solution. Now, we're not saying that's a fundamental set or anything else. We're just saying those are solutions then here is another solution. Why is it? This is the superposition principle. C1y1 plus C2y2 plus C3y3 plus dot 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 plus C sub k y sub k plus yp. Notice there is no arbitrary constant put on there. Okay? None. Okay? Now, if you took the first derivative of all these and the second derivative of all those, okay, these here are going to satisfy that equal to 0. That part will satisfy that's equal to 27. Okay? If this were, that's just a 2 case, this is a k case. But yeah, that's basically what it's getting at. That's also a solution. The linear combination of those other solutions for the homogeneous case plus the particular. Not linear combination, it is a linear combination, but not for an arbitrary constant. Okay? And then it goes back and talks about the linear operator L, which is a sub n d to the n. That goes through all that, and you see that does become true. And that's why they bring up that notation. Okay? It makes it easier to describe this then. Okay? You just have to remember what the notation is and what it stands for. So let's do theorem 4.1.6. Can I erase this? Almost says what we just were saying, but makes it a theorem. It says let y sub p be any particular solution. Now remember, there could be many particular solutions. Could be. Pick one. It doesn't matter. Any particular solution of that non-homogeneous, or I guess non-homogeneous, okay, linear, nth order, differential equation, okay? And that would be non-homogeneous, that's equation 7 before, on some interval I, okay, and let y1, y2, y3, y3, comma, dot, dot, dot. This time we go back to our n, y sub n, because now it's the nth order. So you got n, these functions here, be a fundamental set of solutions to that differential equation that we're talking about, okay, to the homogeneous differential equation. That's with the right-hand side set equal to 0. That corresponds to the non-homogeneous. On the interval I, has to be on the same interval. Then the general solution is going to be, on that interval, is going to be y is equal to c1, y1 of x, plus c2, y2 of x, plus c3, y3 of x, plus dot, 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 plus cn, yn of x, plus yp. Just add it to the end. No constant, no parameter. Just add it to the end. Where all these c's, ci, where I is equal to 1, 2, 3, dot, 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 up to n. Okay. Or arbitrary constants. Notice you don't have an arbitrary constant for the particular solution. Okay? Now, they go through and do a little proof here. It's a nice, concise little proof, and you can certainly do it and see what it comes out. Now, as if there are not enough names that they're given these functions. You have fundamental set, you have general solutions, you have particular solutions. Now we're going to come up with another one, the complementary function. Now this is a function, okay? Now we're finally getting into solving differential equations. I swear it took them so long to get here. Now, Theorem 4.1.6. That's this one that's on the board right now. Okay? We see that from there, the general solution of a non-homogeneous linear differential equation consists of the sum of two functions. One is the general case for the homogeneous, and the other is the particular. Okay? So, rather than calling it the general solution for the homogeneous case, we now name it the complementary function. Okay? The general solution of your homogeneous is now called the complementary function. So this part right here, up to, but not including the particular part, we're going to call this the complementary function. Okay? Now, because this is a non-homogeneous equation, okay? So rather than saying this is the solution, the general solution to the homogeneous case, we just call it the complementary function. A lot easier to say. And then that's the particular solution. So now your general solution for this, Monica's here, and we're somewhere about the top of page 128. And by the way, I forgot to say this when Lauren came in, but I think you already got yours. Yes. Okay. I did finally get in the last of test 1 last time, so now I can return your test 1 to you. Goodness, I'm still short. Okay. All right. Sorry it took so long. Okay. Which means, of course, advertisement time. I need your research papers, okay, and, be working on test 2 as well, because that needs to come in fairly soon too, so I'd like to get that in before I give you test 3, but I'll give it anyway, okay. All right, so that's the complementary function, the general solution for the homogeneous portion, okay. So the general solution for a non-homogeneous will be your y sub c, the complementary function, plus y sub p, which would be any particular solution that happens to work. Okay? So let's go to example 10. All right. They're going to give you a particular solution. I'm sick and tired of them giving it to you. Show us how to get it, okay? This is how this book is done, so rather than turn it over on its head, we'll do it. So here's a particular solution. Wow, how did you come up with this? Minus 11/12 plus, or minus 1/2 x. Wow, okay? It's readily shown to be a particular solution for this non-homogeneous equation. Y triple prime minus 6y double prime, this looks pretty familiar, doesn't it? Plus 11y prime minus 6y, okay, is equal to 3x. Okay. Now I think we had that exact where was it? Goodness, we just did it. Where is it? Did it today, I'm pretty sure. Oh, no, yeah, there it is. Example 9. This is the one we use for example 9, and this is the example 9 was a homogeneous case, differential equation, third order. We know what the solutions are. We did that just a little bit earlier. What we have to do is find that particular solution because this is the non-homogeneous case. Now, they said it's readily shown to be a particular solution. Let's readily show that. Okay? What's the first thing you're going to have to do? To show this is a particular solution for that. Take a derivative, always a good choice. Okay, yp prime is 1/2. Okay, yp double prime 0. Yp triple prime 0. Okay, let's see if what they say is true. Y3p double triple prime 0 minus 6 times yp double prime 0 plus 11 y prime was negative 1/2 minus 6 y, and y was negative 11/12 minus 1/2 x. The question is that equal to 3x? That's the question, right? Said Hamlet. Oh, no. Okay. Those two go to 0. They're 0. Okay. 11 times negative 1/2 is negative 11/2. Okay. Now. Oh, wait. Yeah. So this will be minus 6 times minus 11/2 will be plus 11/2. Yay! Okay? And then minus 6 times a minus 1/2 x would be minus or positive 3x. That is indeed 3x. Okay? So we have shown that is a particular solution for that particular non-homogeneous differential equation to satisfy the 3x. Okay. Now, what's the complementary solution to that? We did it in example 9. This part here equals 0. That was exactly example 9. And those solutions, the complementary solution was C1, remember it, e to the x, plus C2, e to the 2x, plus C3, e to the 3x. Just happened to be, that's the one we did before. So now the general solution for the non-homogeneous case will be the complementary solution, C1 e to the x plus C2 e to the 2x plus C3 e to the 3x. What? Minus 11/12 minus 1/2 x. Your particular solution. Just plug that in at the end. No parameters. No constants, just plug it in, add it to the other, that's your general solution. Still a third order solution because it has 3 arbitrary constants. Those are not arbitrary constants. So 11/12, negative 11/12 is not arbitrary. The negative 1/2 is not arbitrary. Those are fixed constants. They're part of the particular solution. Okay. So far, they have shown you it works, but they haven't shown you how you got it. Well, guess what? We have another superposition principle to deal with first, so let's do that. This is theorem 4.1.7. They don't have enough theorems in this section, do they? Okay, and here's what it is. Let, oh boy, y sub p1, getting so many subscripts here, y sub p2, y sub p3, comma, dot, 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 comma, y sub p, and what do you use there? K, y sub p, k, b, k, particular solutions. Okay? Okay, we said any old one. These are k particular solutions of the non-homogeneous linear nth order differential equation. I didn't need a comma there, but I'll leave it in there. Linear nth order differential equation 7, the non-homogeneous one, on the interval I, corresponding in turn, I put a lot of extra words in here, in turn to k distinct functions and these will be G1, G2, G3, dot, 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 up to and including G sub k. Okay? Now, the y sub p1 satisfies that one, y sub p2 satisfies that one, y sub p3 satisfies that one, all the way up there. That is, suppose y sub p1, I, denotes a particular solution for the G sub I x, where I is 1 to k. Now, right now they're talking as if your non-homogeneous linear nth order differential equation corresponds either to G1, to G2, to G3, to G4, to G5, yeah, up to G sub k. But what they're saying is, what if this is all of those added together? Well then, you add all of the particular solutions together, superposition, no arbitrary constants for any of them. So that then means your particular solution for that particular non-homogeneous form that has all those together, okay, is y sub p1 of x plus y sub p2 of x plus y sub p3 of x plus dot 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 plus y sub pk of x. So in other words, you just add them together. No arbitrary constants though. You're just added together, and this will be your particular solution for the non-homogeneous linear nth order differential equation that has the sum of all those g's. Okay? So you have all your thing at the beginning, and this will be g1 of x plus g2 of x plus g3 of x plus dot 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 plus g sub k of x. So if you had a whole string of these things out here, then get a particular solution for each one and then add those together. That'll be your particular solution. Your complementary solution will be the part that satisfies this. Okay. And then add all those together, and that's your general solution. Okay. Now, the proof they do in a very short order to have that much to take up just stating the theorem. The proof they list is much shorter. Okay. I thought for sure I brought my watch in, but I don't think I did. I must have left it on my desk. What is the time right now? Huh? 9:08. Okay. Would this be a good break time? Okay, let's do that. I usually wait till someone leaves, but okay. So I'm going to put this. All right. Any questions on theorem 4.1.7? If not, let's go and erase this and do example 11. Now, this is a fairly long problem because there's several parts to it. But the solution's pretty, you get all the parts together, the solution's pretty straightforward. They're claiming that yp1 of minus 4x squared, okay, is a particular solution of y double prime minus 3y prime plus 4y is equal to minus 16x squared plus 24x minus 8. Okay? It says verify that. So how do we verify it? First step, take a derivative. Y prime of P1 would be what? Not that hard. Huh? I can't hear. I heard something, but I couldn't make it out. Huh? Negative 8x. Negative 8x. Okay? We'll also need to do y double prime of P1. What would that equal? Negative 8. Okay? So let's plug those into the differential equation and see if indeed that does give us what we're looking for. So y double prime is negative 8x. No, I'm sorry, negative 8. Okay, sorry. Y double prime is negative 8. Minus 3 times y prime, which was a negative 8x, plus 4 times y, which was yp, was negative 4x squared. Okay. The question, is that equal to minus 16x squared plus 24x minus 8? Okay. Well, I can do the minus 8 part and say, yeah, that part works. This will be plus 24x. Yep, that part works. And this will be a minus 16x squared. And yep, that part works too. Yes, that does work. That is a particular solution for that non-homogeneous, ordinary, linear, third order differential equation. Okay. Now, they also want you to confirm that or verify that yp2 is equal to e to the 2x is a particular solution of same thing. The homogeneous part, you might say, the left-hand side is exactly the same thing, but the right-hand side is now 2e to the 2x. Okay? So how are we going to do that? Take a derivative. yp2 prime, y prime of p2 is equal to 2e to the 2x, and yp2 prime, double prime is 4e to the 2x. Okay, now we're going to plug those in. That would be 4e to the 2x minus 3 times y prime, which would be minus 6 times e to the 2x, plus 4 times y, that would be 4e to the 2x. Okay? The question is that equal to e to the 2x? Well, 4 and 4 is 8, minus 6 is 2e to the 2. Well, that's a 2 there, not a, yeah. 2e to the 2x is indeed equal to 2e to the 2x. Yes, it is. So we verified that this particular solution is a particular solution to the non-homogeneous form where that is your g, okay, 2e to the 2x. And they also want us to confirm that yp3 equal x e to the x is a particular solution to all this part is the same, but now the g part on this one is equal to 2x, lost it, 2x e to the x minus e to the x. Okay? That is your particular solution. They want us to verify that is indeed a solution to this nonlinear differential equation. So the first thing we're going to do is y prime of P3. What would that be? Uh-oh, SpaghettiOs. Good old what? What do you think is the root of that? Product rule. And how does that go? E to the x plus x e to the x. Not too bad, is it? So let's now do y double prime of P3. And what does that give you? E to the x, I'll buy that one. Plus e to the x, I'll buy that. Plus, say again, x e to the x, okay? Which simplifies to be 2 e to the x plus x e to the x. Now let's plug those into our equation. Right up there. Y double prime was this one. 2 e to the x plus x e to the x minus 3 times y prime. That would be minus 3 e to the x minus 3x e to the x plus 4y. That would just be plus 4x e to the x. And the question is that equal to 2 e to the x plus x e to the x. Well, let's see. Here's the 2 e to the x. Well, I must have left something out. I'm not seeing it. I see this part equals that part, but I've got a negative 3 e to the x from negative 3 times that. Did I copy it? No, I did that right. Oh, I'm sorry. I wrote down the problem wrong. No. Yes, I did write that. Where did I get that? I was looking at the wrong line. Sorry about that. This is not the equation. Okay, sorry about that. My eyes went down a line or two. The nonlinear the non-homogeneous part is 2x e to the x okay, minus e to the x. Y'all got to keep up and keep me from making dumb mistakes, right? Okay. Now, with that being the second part, the g of x here, you have 2e to the x minus 3e to the x. That's minus e to the x. Let me write this down here. You know, I had written it correctly in the line above. I'm getting myself completely confused here. All right. Okay, sorry. I see what I did now. Let's go back. This part is, this is my y double prime. This is 2e to the x plus xe to the x. This is the part that should have come down here. 2xe to the x minus e to the x. All right, now we got it. Okay, sorry. I wrote this part here rather than that one. Okay, now we got it. So 2e to the x minus 3e to the x is minus e to the x. That checks out. That adds to that. And then we have xe to the x minus 3xe to the x. Well, let's do the pluses first. X plus 4 is 5xe to the x minus 3e to the x is 2xe to the x. Yes, those combine as well. So sure enough, that works. Okay? Now, what we haven't done, I don't think we've done, y double prime minus 3y prime plus 4y. Have we done that earlier? I don't recall that we have. I think they're going to let me know if they did. Okay. All right. I was reading more into the problem than they really have here. Okay, it follows from figure 4.1.7 that we just did that the sum of these solutions, this one plus that one plus that one, okay, will then be a solution to this. I'm going to write it here in the middle because I have a little more room to write. Y double prime minus 3y prime plus 4y is equal to the sum of these. Minus 16x squared plus 24x minus 8 plus 2e to the 2x plus 2xe to the 2xe to the x minus e to the x. Okay, if you had that differential equation with the sum of all three of these g's being your new g, then your solution of this will be whatever your solution is here, and they just basically well, they just say trying to find where then their particular solutions will be the sum of that one, yeah, plus this one, plus that one. Okay, that now wait a minute. Here they threw in arbitrary constants. Earlier, I'm sorry. that ends this one. This linear differential equation, the particular solution will be the sum of those solutions. Okay. Now, their note here was confusing. If the particular solution, if y sub pi is a particular solution of your, this is now they're referring to equation 12, which is your, in theorem 4.1.7, looks, it just has gi there now. Then the particular solution, you do put arbitrary constants in if your gi of x is some linear combination of the g of x's. So, I mean, why are they throwing this in now? What if you had that is your non-homogeneous part? What if you had an arbitrary constant times that? Like you could have pulled out a -8, okay, or anything else, and had plus c times 2x squared plus 3x minus 1, okay, or something like that. And this one down here, you just had some arbitrary constant, c, for instance, 2 times 2 e to the 2x. And then this one down here, some other arbitrary constant times, c3 times 2e to the x. If these were arbitrary here with constants in them, then you can use those same arbitrary constants in your particular solutions. Here, here, and here. If that had say a -8 in front, then this would be a -8 times this. If that had a 2 in front, this would be 2 times this. If that had a C3 in front of it, then this would be C3. So you do put arbitrary constants in to particular solutions if your general, the g of x's, were arbitrary constants. Okay? Bizarre place to sort of stick that in at the end, but that's what they're saying. Okay? Now, their remarks at the end of the section, I usually try to avoid those because they can get really deep, but it is introducing some new terminology to you that, frankly, I don't usually use, okay? But maybe some of your majors will use these. So let's say we have an nth order linear system, non-homogeneous, whatever, okay? The n time-dependent function, and these are all functions of time, not of x, okay? The n time-dependent functions, y of t, y prime of t, y to the n minus first prime of t, are called the state variables of the system. Now, why they picked that name, I'm not sure. Recall that their values at some time t will give the state of the system then, so that may be why they call it the state variables. The g function at the end, the non-homogeneous part, is called the input function, or sometimes called the forcing function. Your solutions for that, y of t, are then called your output or response to the system. So if you put in an input there, what output do you get here? Okay, and that's your general solution. Just a little bit of nomenclature. So homework exercises here. 4.1 I've assigned for several days now, either 1 or 3 or both. Either 5 or 7 or both. 9 and 11. Okay? And by the way, these answers to the odd number problems, most of those are in the back. 13. And then 4.1.2. Any of the odds 15 to 21. Any of the odds 23 to 29. Okay? And then what we did today, and we ended 4.1.2 today, so probably the last part there you could do. 4.1.3, the non-homogeneous equations, any of the odds, either 31 or 33 or both, do 35. Okay? And then the discussion problems, generally those answers aren't in the back, but some of them may be, so you can do any of those you want to. All right. Finish finally 4.1. That was one long section. Okay, now, let's erase this. How are we doing on time? I didn't bring my watch. Okay, good. Okay. Let's talk about reduction of order. All right. In that preceding section, we saw that the general solution of a homogeneous linear second-order differential equation, that would be something like this: a sub 2 of x, that's a coefficient function, times y double prime, plus a sub 1 of x, y prime, plus a sub 0 of x, y equals 0. Homogeneous, okay? That's a linear combination of two functions. Second order, you're going to have two arbitrary constants, okay? So your general solution here will be a c1 y1 plus c2 y2. Those are both functions of x, okay? Where y1 and y2 are solutions that consist of a linearly independent set on some interval I, okay? Now, they're looking ahead now. That was what we did last section. Beginning in the next section, we examine a method for determining these solutions when the coefficients of the differential equations are constants as opposed to variables. This method, which is a straightforward exercise in algebra, breaks down a few cases and yields only a single solution, y1, of the differential equation. It turns out that we can construct a second solution, y2, of a homogeneous equation, even if the coefficient of one are variable coefficients, one are the variable solutions, not constants, provided we know a non-trivial solution, y1, of the differential equation. Non-trivial, not the zero. Okay. The basic idea described in this section is that equation 1, this one right here that I've written here, can be reduced to a linear first-order differential equation by means of a substitution involving the known solution y1. Then a second solution, y2, is apparent after the first-order differential is solved. Blah, 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 right? What in the world are they talking about? All right. Suppose y1 denotes a non-trivial solution 1. y1 is defined on the interval I. We seek a second solution, y2, so that the set consisting of y1 and y2 are linearly independent on that interval. Okay? Now, if they're linearly independent, and it's a second order problem, the quotient y2 divided by y1 is non-constant. Remember, if the quotient of y2 and y1 is a constant, they're linearly dependent. They've got to be. So if it's not a constant, then you have some other variable. There's some variable included in it. So the condition here is that y2, the one we're looking for of x, divided by y1, the one that somehow we knew already of x, is some new function u of x. Not a constant. Not a constant. Okay? So therefore, y2 of x is equal to u of x times y1 of x. But we know y1 of x, right? Okay? That function u of x can be found by substituting this thing that I just wrote down here into the given differential equation. That's called a reduction in order. Okay? So let's do example 1 and see if we can make all those words make some sense. Okay? Here's a function. y1 is equal to e of x. Good old function, one of my favorites. And it says, notice that is a solution to y double prime minus y is equal to 0. You buy that? Because what's y prime? y1 prime. e to the x. What's y1 double prime? E to the x. So e to the x minus e to the x, sure enough, is 0. Okay? So yeah, we know that is a solution, a very simple solution. Okay? Now, so that's going to be our y1. Our y2, we know it's got to have another solution. Linearly independent solution to form that fundamental set. I couldn't think of the word. This y2 of x is going to be some u of x times y1, e to the x. Okay? Now, and this is all true on the interval minus infinity to infinity, because e to the x works everywhere. All right. Now, that's going to be our y2. Okay? Now, we want y2 to solve this too, right? So what we got to do is y2 prime of x, and what's that? Now, we don't know what u is, but we will deal with that. So that's a product rule thing. You tell me how to work it. Okay, say that again. Okay, e to the x I heard you say, and what did you say the second part was?
Plus
E to the x, is that what you said? Okay. Now, I'm not sure I quite buy that completely. What's missing? Say again? No, you're not integrating. Okay. If you are differentiating this, it's the first times the root of the second. I'll buy that part. But then it's the second times the root of the first. This needs a u prime. Okay. So that needs a u prime. U prime of x. Okay. Now I'll buy that. Not for very much, but I'll buy it. Okay. Now. Okay. Okay. Where are we? All done. Okay. That's the y prime. Let's now do y2 double prime. Okay. Hope you can read my writing. I stuck it in there. Let me see if I can make it a little more visible. It's not much better, but a little bit. Okay, now let's do y double prime. What would that be? Help me. Anybody? Another two product rules now. First one, then another. You tell me what the first one would be. Say that a little bit louder. U double prime of x, e to the x, that's the first part of the first part, plus this first times the root of the second, which is u prime of x, e to the x, right? Okay. Now let's do the product rule on the second part. And what would that be? Plus, anybody? Product rule? Second? A little u prime of x, is that what you said? E to the x plus u to x, e to the x. Got it. Okay? Now, let's combine like terms, you might say. Let's just pull out an e to the x. E to the x is there everywhere. What do we have left? U double prime of x plus 2 u prime of x plus u of x. Okay. That's your y2 double prime. Okay? So that's your y2 double prime. That's going to be on the left. So this thing right here, minus y2, which is this thing right here, is u of x, e to the x. Okay? Now I regret that I wrote it this way. That's supposed to equal to 0. Okay, now obviously the e to the x, u e to the x, minus u to x, e to the x, that's going to add to 0. So that's out of there. So what we have now is e to the x times u double prime of x plus 2 u prime of x is equal to 0. Okay? Now obviously e to the x is never 0, so you could divide that out. Okay? So what we wound up with is u double prime of x plus 2 u prime of x is equal to 0. Okay? Now, that's what they have here. And since e to the x is not 0, that just leads to this. Okay? U double prime plus 2u prime equals 0. Now, here's where you get your reduction in order. Let's come up with a new function. Why not? Let w of x equal u prime of x. Okay? Now what do we have here? Then w prime of x is equal to u double prime of x, right? Now your new function now will be w prime of x plus 2 w of x is equal to 0. All right? That's now a linear first order differential equation. It went from being second order to first order. Okay? For this new function w. Okay. Now, you remember how we solve a linear differential equation? Whoa, this takes us way back. How do we do that? Say again?
Make it p of x.
A p of x. Make this the p of x, right? And yeah, we can do that and then do, but yeah, wouldn't we be able to do this by separation of variables? Wouldn't that be a little bit easier? I don't know why they do the other way here. Except it's a pretty easy substitution, but wouldn't separation of variables do it just as easily? I want to try a second separation of variables. Let's just see. Let me rewrite this function here as dw dx, that's w prime, plus 2w, I'll just leave it, plus 2w is equal to 0. Okay? So let's subtract 2w from both sides, and you have dw dx is equal to minus 2w, and then write it in differential form, dw is equal to minus 2w dx, okay, then divide by w, so you have dw over w is equal to minus 2 dx, right? And how do you integrate the first side? What's the integral of dw over w? ln w is equal to minus 2x. Okay? Now, exponentiate both sides, and that gives you w is equal to e to the minus 2x. Now, to me, that's better than going back and doing a linear thing. You get the same thing, okay? E to the minus 2x. That's going to be your w. Okay, say again. And you do a c. And actually, let's make it this way. Plus c, do it up there when you first do that. And then when you exponentiate both sides, do a log c. That's what we do. Log c. And when you exponentiate everything. Anyway, the c1 goes in front. Okay. Log c, sum of two things is a product. So the c1 goes in front. And that is your w. c1 e to the minus 2x. Remember that w is equal to u prime. So now we have u prime of x is equal to c2 e to the minus 2x. Okay? Well, let's do the same thing to that. This is du dx, so this would be du is equal to c2 e to the minus 2x dx. Right? And then we'll integrate both sides of that, and you get u is equal to, where did I get a c2? That's a c1. Sorry. Okay. Duh. And when you integrate this, you get a, I'm running out of room here. Yuck. A negative c1 over 2 e to the minus 2x plus some other c2. Okay? And then you can make that a new variable, a new constant if you want to. But actually what they do, I'm sorry, there's just not enough room on this little page. What's that? Yeah, are we out of time? Okay. I'm sorry, I've run out of room and we've run out of time at the same time. If you see that, okay, remember then that y is u to x, e to x, so you got another step in there. And if you will, go on and finish example 1. It's not that complicated, but you can go on and finish that, and we'll start next time at the general case at the top of page 133. Okay? Let me give you, I think, maybe a couple of home, yeah, this is a very short section. I think you can do some of the odds 1 through 15. If you can't do them all, hold off. We'll come back and finish up those later. Okay? So try to finish example 1 and start looking at the homework exercises 1 through 15. We'll make a general case and move on and finish this next time. Good deal. Have a good weekend. Working on those papers, right?
It has to be on, it can be on any math subject, like any.
Yeah, try to get differential equations into it.
Okay.
Right. It can be a person, it can be an application, it can be anything to do with differential equations. Okay.